Okay, I don't know what this is picking up. Well, here we are. It's Tuesday afternoon. Trash man's out there. Pepper is on the floor in front of the heater. We got the windows open, nice cool breeze. And here we go. So from now on, the Zoom wrap up comes first, and then the screenshots. And maybe I can improve screenshots from class. I apologize here because here's the trash truck. Um, okay, so watch. I'm going to try, and these are going to take. It's going to take longer because I'm not just going to have like I was just doing screenshots and explaining what happened in class, but that was not helping. Um, that was not helping. Students as much, virtual students, if you weren't there. So this is going to be me trying to teach you. So it's going to probably double the length. Apologize. I guess you can always fast forward. Okay. So this is share the screen here. And this is for class number 6, packet 2, Tuesday, the 20th of October, in the year of the COVID. All right. Little review here. We talked about this in the last wrap-up video, so go back and look at that. I went through this in class today just to show you that, and this is leading. The areas here are the fancy word. The $5 word is area graph, or this is the areas of these. We're taking the area of each one of these sections. The $50 word is integral. We're taking the integrals of these sections. When you find the area under or above, under a curve, and this is not a curve, but under a function, it is the integral in calculus. And in calculus, you also have things called negative areas, and that's the blue. Okay, so that's sort of a review from yesterday. Oh, okay. And then also yesterday, we did this derivation. I know this seems out of place. The reason why I think at the time we were on to something else, and I could teach. I think I have enough material to teach 3 to 4 years of physics, like every day giving you new stuff. But I kind of cut it down to 1 year. So I just kind of every year I kind of hit and whatever. I mean, as long as we talk physics every day, I figure we're doing good. But this is in the repertoire. This derivation should always be brought up every year at some point. And so it's a bridge equation. It's probably the most important bridge equation. We haven't used it yet. We use a lot of V is equal to R omega. But that's, if you can get that, then this is just an offshoot of that. Anyway, so being able to do these symbol manipulation is extremely important in physics. So many equations come from derivations. All right, we talked about it yesterday, breaking you up into theoretical physicists versus empirical physicists. And that's a virtual special. Didn't talk about that in class. So today's physics, there has to be some advantages to being virtual, right? Sometimes you get the more relaxed ASCII without, all the. I'm just sitting here in my study in the nice heater and the cool air, and Pepper snoozing over there. So this is due on this is to be submitted not on Thursday night as original, but I pushed it back to Sunday night. Like I say, I'll never bump them forward, but I will push them back. And the reason is I don't like 2 things due on the same day. And really, in this case, it'd be 3 things because the packet's due on Thursday, the 150-point packet, the 300-point test, and then I'm going to throw another assignment on top of that. So this one is due Sunday night, 2.1. So in class today, we went ahead and worked on 6 and 7. I know there's supposed to be homework, but I felt like this would be good before the test as well because it's sort of a good review. A lot of times the first sheet of a packet is sort of a review of the last packet. Anyway, this is a really good review, this sheet. I need to work on some of my problems, like obviously I've got to, I got to spell sweeping right, an I right there. sweet pong. So there's a couple typos, and I can do some extra work. And if that dog, okay, so there's this dog in the neighborhood that poops in my yard. It can't be that dog. This is some big poop. Man, people who, if you walk your dog and you don't clean up the poop, that is rude. That's one of the rudest things. If you don't, I mean, take a little bag with you, okay? So there's this dog that I'm gonna find him eventually. There's this dog that poops in my yard. Anyway, so back to work. So when I was in Tulsa, we were doing this. I was sitting on the lawn chair and looking over. I think my wife accused me, this is a few years ago, she accused me of, says, do you ever not think about physics? It's kind of hard not to think about it because it's all around you. But this time I was trying to quantify some things. Okay. So let's look at number 6. We'll do 6 together, and then 7, we went to the board. So I'll let you know which ones are board work. And for you virtual kids, for board work problems, you should definitely try them first. And then that's what we do in class. And unfortunately, I can't sit there and give you hints, but and you can't talk with somebody else while you're working them. It'd be kind of cool if we could figure out a way to do that so that you're also talking to other virtual kids while you're working problems, because that's a key to physics, is being able to discuss it, right? All right, rather than sit and listen to me. So in 6, we have a train going east. All right, so it's heading east this way. I'm going to do a map view, looking down on it. Okay, so there it is. And once again, I apologize because when I wrote this a few years ago, I did not think we were going to be in a pandemic. And so I didn't think you'd be turning in papers by taking pictures of them. And so I thought, well, let's just use the back of the page. Who cares, right? Well, now it's a pain in the butt because now you got to take, instead of taking one picture of the front, you got to take 2 pictures. I had one student take 7 pictures of 2 sides. Don't do that. Okay, I don't want to look up there and see 7 pictures of 2 sides of a page. One side, one picture on one side, one picture on the other. But I apologize. I screwed myself, tell you the truth, because now I got to download 2 pictures per student. But live and learn. Next time, anticipate a panic. So here I am. I am looking south. So there really is. I really was doing this. There is a train track that runs south of our campsite we stay at there. And so I was watching it, and I follow that train with my finger. So dash, dash, dash. I lock on to a train car. And then so I point. I don't know if you can see me in this. Anyway, so I'm pointing, and then I follow it until I go to 0.05 radians at a rate of 0.05 radians per second. And I think I'm going to rewrite this as well, because it shouldn't say, you should always leave omega in terms of pi. And that's my bad. You don't always see it. I'm saying in my class, I think it makes sense. And you'll find it though in physics problems all the time, not in terms of pi, but I just think that we should stay. Plus it emphasizes we're talking circular motion, not. And then I had a student ask a good question. They said, wait, the train's not going in a circle around you. Why are you using circular motion? Because my arm, I wish you could see me, but my arm is rotating. As I'm pointing towards that train, my arm is rotating. Okay. So the omega here is 0.05 radians per second. Okay. What else do I know? I know it's a quarter mile away, so R is 0.25 miles. I'm going to go with 2 siggies. That's what Logan did in class, and I think that makes sense, to leave your answer in 2 sigs. Is that it? If my arm is sweeping out an arc, what's the estimated speed? So I want to know what is V. Always put in there what you're trying to find. So V. Okay. Well, let's take a look. So I'm going to, so my picture will be in black, and then I'll start doing my work. The equation I'm going to use here, my bridge equation, of course, is V is equal to omega R. And so I just plug and chug it almost, except that there's a little unit issue. So I'll go ahead and lay out the unit analysis. You don't have to, okay? I lay out the unit analysis. Man, if you get like what Loom does, teachers use Loom, and that's like a Google slideshow, right? And then their little face appears down there. I wonder if my face, I don't want my face to appear, but sometimes I need my body, my hands. I need to go back and look and see if my hands appear. Okay, so that second one is going to be squiggly because that's going to be into my givens. So to find V equals, and there's my omega and there's my R. Okay. So omega here is 0.05. And I'll just leave radians off. That's kind of cool about radians, is it really nice. It's really easy unit analysis when an omega is involved, or a theta, because there's no unit stuff to worry about. So 0.05 radians or blank per second. Okay. Really, it's S is the abbreviation for seconds, but when I do that, students think it's a 5. So I go ahead and write out SEC. R is just remember, use the units that are given in the problem. So R is 0.25 miles, MI, not M. M is meters over 1. Well, I'm going to end up in miles per hour. So it looks like I got one quick conversion to do. And it's okay because seconds and hours, we see that so often. I don't like you to contract units. Like I don't want you to, I want like a unit like this conversion part over here. I'll highlight that. I want the conversion part, this yellow part, to be in simple forms of 1, or what I call quanta of thought, this little tiny known things. Well, like some students will try and combine inches in a mile. Well, who knows? No one knows inches in a mile, those kind of things. And don't tell me you do, because nobody knows that. Just off the top of their head. I mean, there's something wrong with you, I think, if you know how many inches are in a mile. You should seek therapy. Now, feet in a mile is 5,280 feet. Well, everybody knows that. Okay. I'm not a nerd. So I want to go, let's get this in terms of miles per hour. So I will allow you, what I was trying to get at there, I will allow you to go ahead and use this conversion. So it's because it's so common, this contraction of conversions, 3,600 seconds in an hour. Now, if you want to say seconds in a minute, minutes in an hour, I feel free, but I am saying it's okay to go ahead and go seconds in an hour. Okay, you punch, punch, punch. And students have been doing this all day, so I should remember. I think it's 8.75. I'm going to go ahead and pause it to make sure, but I think it's 8.75. No, I'm thinking of number 7. Oops, gave it away. Hold on, let me pause. All right, so I'm back. It is 45. It ends up being 45 miles per hour, which is reasonable. If I got 450 miles an hour, I know I messed up somewhere. Okay, so let's go on to number 7. Number 7, now this is the one you win the board on. So you need to try this one on your own first, okay? Pause it and try number 7 on your own. And I really did this. Okay, I'm back from pause now. I'm assuming you paused it and you tried it. And now let me give it a shot. I really did this. I sat in my lawn chair and I looked at it. I saw 747 flying overhead, and it is flying at, let's go black for the setup. It's flying, I don't know, this way. And I know that 747s, once they reach their altitude, they typically go at V equals 550 miles per hour. So here I am. I'm down here now. This is a, by the way, this is a profile view. Profile. As opposed to a map view. So I'm looking at this one from the side. So it's a profile view. I'm going too slow for you. Maybe hit the fast forward. Turn off the sound. Oops. Okay. Profile view. All right. That is irritating. All right. It should snap. This little ruler should snap at certain points. So here we are. And now I'm once again, my finger's right there. And then I follow it for a little bit. Well, I can tell you how long I follow it. Pi over 3 radians. That's a long ways. Wow. Pi over 3 radians. Oh, okay. Okay, that's not that far. That's pi over 3, what is that, 60 degrees? If I'm thinking right here, I think it's 60 degrees, yeah. Is that right? 1/3 of 8, yeah, 60 degrees. So it's going pretty big. 60 degrees is like that. So I think my drawings in class were bad. So it goes, my arm rotates, delta theta is pi over 3. So I guess I'll have to use this drawing. In 1 minute. And so t equals 1 minute. So a student said, well, should I use this the new equation we derived, delta S equals omega RT? I said, yeah, you could do that, but that's sort of the long way to solve it. I think it is solvable that way. I'm just going to go back with the shortcut with the easier one, and just say that, oh, sorry, I got to put what I'm trying to find. I'm trying to find the height. So I want to know, what is R? R here is question mark. Yeah. Now this looks funny because the R is not as big as it normally is. When you have something that's much, this is once again a virtual student special, but when you have something that's much, much bigger than what you're showing, here's how you show it. Virtual exclusive here. You put a little then there. And that says this line is actually much longer than I'm showing you. Okay. Anywho, so now back to work. And if you needed to pause it again, now you want to go and solve it. You can't just sit and watch me do this. You've got to take an active role in watching these videos. So we have V, otherwise all is lost. You're fooling yourself thinking you understand physics. V is equal to omega R. Okay. Omega is delta. So V equals delta theta over T times R. Okay. That is omega. So then now I just plug in V equals pi over 3 over 1 minute times R. Now, oh, we know R. No, we don't know R. Hello. Daggone it. I should pause this and back it up, but I'm not going to. I made a mistake. Crucial error. The crucial error here is I did not solve for the variable. I should solve for the variable in symbol form first before I start plugging in numbers. So that's my bad. I was thinking I was solving for velocity. I'm solving for R though. So R is then, if I solve for R, I'm going to get VT over delta theta. Once again, I didn't solve it this way in class, but I should have. Once again, I'm going to make this my screenshot. Is that right? Yeah. Okay. I reversed it and then, yeah. So this, I would box that in because you're going to get probably 6 out of 10. If you stopped right here, you'd probably get a 7 out of 10, to tell you the truth. Now we just plug in numbers. So R then equals, I'm going to do this as a unit analysis because I do have some unit issues. So let's go ahead and I'll change the colors now. Now we'll go red. So it's next phase of the problem. This is the kind of the number crunching where I start to add numbers in there. We're going to follow a method later on called CL-DEPA. And so we're in the, now I have 3 variables. So then I'm going to put my squiggly. Okay. Daggone it, should have this in class. That was stupid. V, T, I mean, we did it the other way. 1 over theta. We didn't do this delta theta. We didn't do it this smartest way. And I'm doing kind of a gold standard approach here. V then, so V is 550 miles an hour. So you just go ahead and plug the numbers in as they are in your problem. 550 miles per hour. Time is 1 minute. Didn't flip it or anything. Over 1. And then delta theta does get flipped. So delta theta is pi over 3. There's no units to it. So pi goes down here and 3 goes up here. I got to flip it, 3 over pi. And so I want to end up in how far above my head is it? In, didn't say how far above my head. Didn't say what, that was stupid. It didn't say what units to use. Ah, God, they got to change this again. I got to fix this. Now that's a good dog. I bet that dog, that's a candidate there. It's a big dog. All right, we'll keep an eye on it. So let's go ahead and get it in terms of miles. And because there's no reason why I shouldn't, because I've already got miles here. So should get my green kill pin out. Purple, and then I'm going to go with the green kill. Okay, the green kill pin. Got her. All right. So purple for my conversions. Let's see. So I'm going to leave and then green for my kill pin. But on the kill green color, I want to keep the miles. I want to kill everything else. I want to kill the minutes. I want to kill the hours. So that gives me an idea of what kind of conversion to put in there. I don't want to go hours to seconds, right? So I want an hour over 60 minutes. And there you go. Let's get out the green kill pin. Minutes go away. Hours go away. I'm left with miles. Therefore, I must be correct. And now I just got to punch in my numbers. And let me pause it while I punch. You should punch in your numbers too. Okay, so you can see on the screen there that I got 8.75 miles high. And that seems high, but it's not that's not extraordinarily high. So 747s want to fly up that high because the atmosphere is thinner up there, less air drag. We had done earlier this year, we've done a problem involving the formula for air drag. The RA equals 1/2 d rho AV squared. And so if I can get that rho, which stands for density of the medium, which in this case is air, if I can get that rho to drop by, 70%, 75%, then I drop my resistance, my air drag by 75%. So it makes sense. A lot better fuel mileage up there. So there we go. I'm going to take a couple of screenshots of this, so I'll pause while I do that, and then we'll get back and work on 2.3. All right, so resuming here, moving on to sheet 2.3. This is how far as we got on the wrap-up video yesterday. It's where we picked up the action in class today. So let's start off by, this is that Slappy the Clown trying to get back to his trailer. So let's start off by filling in these questions. It says, what's Slappy's overall distance he traveled? Well, he went from 40 to negative 40, and then negative 40 here to 40. And then he went from 40 to negative 20, then negative 20 to 20. So when you add all those up, the path, remember, it's not a zigzaggy path. It's a straight line back and forth. We're showing it through time. So he went, if you add it all up, he went 240 meters total. What's his overall displacement? Well, displacement, remember, it only cares about where he started, which is at 40, and where he ended, which is at 0. So that is negative 40 meters. And then what's the fastest velocity? The fastest velocity, it looks like it's on positive 8. So 8 meters a second. What is the slowest velocity? Some people say negative 6, but that's not slow. That's fast, just backwards. So 0 meters per second when he wasn't moving. And then what's the overall average velocity? Well, you could take these, you could do it wrong. You could take these numbers and add them up and divide by 6. But that, we know that's wrong because that would be a non-weighted average. This is a weighted average because he did not spend the same amount of time doing every one of these intervals. Now, normally in a normal year, I have test questions on this, but I think that's going to be something that's just going to have to suffer. We're just not going to cover it. This idea of weighted versus non-weighted averages. Anywho, the statistics is becoming a big part of physics now. You all, if you're going to go into physics or any kind of science, you really have got to take a stat class. At Norman High School, it's Demis Adair, because you need statistics now more than anything. If you look at there's the old saying that there's lies, damn lies, and statistics. And statistics are lying to the American people all the time now with COVID, because it's giving us, it depends on what statistician you subscribe to, whether it's the Federalist Society or it's Mother Jones. They'll have their own stats and they can make the thing look about any way they want. So anyway, statistics are really important in science now. I didn't take a stat course till I was in grad school. It wasn't necessary back then. Okay, so the average velocity, the fastest way to solve it, the easy way, if there's a graph involved, is just take the first point and the last point, subtract those, so that's negative 40 is how far he went, and then divide that by how long it took him, which was 110. So you're looking for the slope. And so it's going to be, that is to show it the work there, that's negative 40 meters divided by 110 seconds. Okay. And I'll pause it to calculate. So got it all nice and neat there, negative 0.36 meters per second. So if Slappy had just not kept overshooting his trailer, he could have just slowly walked. It's a real slow walk. That's about 4 times slower than the average human walks. And could have just walked super slow and taken 110 seconds, but finally got back to his trailer, okay? Without going back and forth, back and forth, back and forth. Then it says represent this, which we did, the blue line up there. All right, now the next thing is we've got to come up with the slope graph for this. So let's plot that slope graph, and we've done one of these already, but just to show you here, so coming down, this whole thing, by the way, is called a duet. And the simple word for this is slope graph, but what we're really doing is this is a derivative. Now it's a very simple derivative. In fact, it's the simplest possible derivative. But derivative is the $50 word for slope. Okay. So you can tell your parents, if they're engineer types or scientists, that today we're studying derivatives, which I think will make them happy. All right. So they're called a duet because they correspond. They correspond through time. All right. So here we go. So my time axis is the same. Now I got to set this up. I want, let's go with black again. Hold on. I want, I'm losing my train of thought here. All right. So I want this, I want to figure out where to put my first and fourth quadrant. Well, I'm plotting velocities. When I look at these velocities here, I have my maximum, my range here is a +8 to a -6. So it looks like I'm going to fit these in. If I make this 0, let's blow this up a little bit. If I make this 0 here, get out of there, 0 here, and that's 5, 10. Remember, this is V. You got to put what the symbol is and what the units are. V at meters per second, or you lose a point, -10. And then on the time, we're going to leave the time the same as it is up top so we can correspond. So I'll go ahead and let me pause it while I fill in the times. Okay, so this is like Martha Stewart, you know, when she pulls the souffle out of the oven. And so it's all set up now. So go ahead and catch up. Got to have you have to have the times marked. I did every 20 seconds. Okay, so now we're plotting the slopes, which is derivatives. We're plotting those slopes of the graph above. And so I have this handy dandy. I don't need that graph above anymore because I have this handy dandy table here. So now I'm going to go ahead and once again, I'll pause it and let you should pause it too. And then you do it. That's what I made the class do. We didn't go to the board on this, but I did wait and let them try it. And then, you know, I can't walk around the room a whole lot because of the whole COVID thing, but I kind of gave them time to try it and to show each other. We're trying to make this as much of a community project as we can. That's the trick with virtual. How do you make a community project so you're not a bunch of lone rangers? You need to, with this Facebook group, Unit 5, is it? You need to start talking to each other there. Huh. But it'd be nice if it's a question about a worksheet, then I want you to share that with the rest of the classes. So that'd be in Unit 1 or take home test Unit 2. Unit 5 is there for just logistics. You ask me questions, talk to each other, you know? All right, so I'm gonna pause it and do this, and then you do it as well. Okay, so I'm back. I'd like to know next Monday when the virtual kids get together, when we do our Zoom, whether me pausing it and then, because I'm trying to shorten the time, you know, it shortens the amount of data that I have to use up, and it shortens the amount of time you have to watch it. But maybe you want to see me think as I do it. I don't know. Anyway, so there we go. We did that. And now we have a step function that's piecewise, but it's a step function. So there's really nothing new yet today. It's just another practice at this because it's such an important thing because it does lead to derivatives in calculus. Now, the next thing we did was went ahead and just for grins, we colored in the rectangles. So we did the stalactites and the stalagmites. So I'm going to color in these rectangles, and to try and save time, I'll pause it. But when I pause it, you ought to try and do it on your own. So we're just coloring these in. Remember, this is the base here is like the cave floor. And then there's a cave. There's two caves here. So this is the floor or the ceiling. And so for the first quadrant, the stalagmite grows up. And then for the fourth quadrant, the stalactite grows down. Okay, bring back some childhood memories for you. All right. Am I paused? No, now I'm paused. Okay. I just know I'm going to get this mixed up. I'm going to be talking through the pause. And then, anyway, so I went orange in this case for positive, and I went purple for negative. So we're not going to write these in, but you could because, well, since this is a video, a wrap up video, go ahead and do it. I'm going to pause this, but you should try and figure out what each one of these areas is. You could do base times height, or you can just look at the graph above. So let me pause it, write it in there, because this is the one I'm going to keep, make it look nice, and then we'll talk about it. Okay, so what I've done here is, and this is the first year I've ever done this. Normally we save this for the next sheet, but more practice, I suppose, is important. So here, look at these numbers down here. I got like that little slice there is a pink is negative 20 meters. That rectangle is negative 60 meters. Then we have a positive 80 meters, then a negative 60 meters, then a positive 20 meters. Well, where are they getting those numbers? And so you say, wait a minute, okay, for the derivative graph, that those numbers are showing up like here's negative 20, that shows up here, negative, it's my drop of negative 20. Here's negative 60, so there's my drop of negative 60. Okay, so, you know, mind blown. There's 0. Here I'm rising 80, and that shows the 80. So it's another way of interpreting it. Here's negative 60, and here's positive 20. So tomorrow or the next day, we're going to start the, actually, the next day, that's test, but next week, I'll introduce it tomorrow, but we'll start to do the finger dance. And that is, you have to kind of interpret. So both these graphs are saying the same thing. It's just that the bottom graph is like almost encrypted. I know in geophysics, we would do fast Fourier transforms. It's not quite that, but it's looking at things like in either a time domain, and you do a fast Fourier transform and it turns it into a frequency domain. Well, this is both of the time, they're both time domains, but one of them is position versus time, and one of them is velocity versus time. So we basically put it into a box, and that box pops out a derivative or a set of derivatives. And that's what these are, which is slopes. So it's kind of cool. Both graphs are telling you the same thing. Now, the faster you get that in your head, the faster you'll start to understand calculus. Okay. So now that's it for that. Now we're going to go on to this last thing we did in class. We're almost done, I promise. And this last thing we did in class was we looked at the back of the sheet. Now on this one, we start with the bottom graph, and this has nothing to do with Slappy, by the way. So we start with the bottom graph and we work our way up to the top graph. So first thing I want you to do is this, they're almost done, I promise. But the first thing I want you to do is to color in, hit pause in a minute and color in lightly. Do it on your own this time and see if you do it right. Color in the rectangles down here, okay? So I challenge you to do it on your own first, and then I'll do it, all right? So pause. Okay, so here we are. Did you do it right? If you just sat there and waited for me to do it, then you learned nothing. But if you tried it and did it right, pat yourself on the back. So we have positive areas and negative areas. Notice that it's stalactites and stalagmites again, and they start from the border between the forward, which is the first quadrant, and the backwards, which is the fourth quadrant. So it looks like we're going to stop here in a second, but it looks like I'm going forward for a while. I have a positive slope of 10, which is like Usain Bolt speed. I do that for 8 seconds. Then I turn around on a dime. There's no that's what I say, it's a piecewise. This, by the way, is an impossible. Piecewise functions are physically impossible for the most part. And step function is a form of those. They're just a mathematical, fantasy. We're going to get to more realistic, but those are harder. I had one student in AP Physics one year say, I like this, but the more real the situation gets, the harder the math. And that is very true. He's now an engineer down in Florida, doing very well. So then we go negative. We back up for a while at about half the speed. I'm just interpreting it. I'm getting a feel for this graph. So it's like you have a positive slope, then you go to negative, half the slope. Then you're going to sit there like Slappy did. You're not going to do anything for 5 seconds. Then you're going to go slower at looks like about 7 meters a second forward. And then you're going to turn around and go once again, blazing speed backwards for the last 10 seconds. Okay. So it looks like it's going to be twin peaks, 2 peaks, up, down, flat, up, down. So it's good to do that kind of stuff, to interpret what the graph should look like, what the feel of it is. Well, we're going to pause it right there for today. That's as far as the class has got. I don't want to get you too far ahead or too far behind. And thanks for, well, let's stop the sharing. So thanks for watching. Let me know. You got to give me feedback on the Facebook group or in the Zoom Monday night, next Monday. Let me know how these are going for you, because you're my kind of my guinea pigs. I want to do this when I retire. I want to be able to teach kids all over the world just some basics of physics. So through this medium, right? Okay, so I'll see you guys next time. Have a good Tuesday. I can't say Tuesday. Who knows what day it is when Jair watches this, or Sven watches this in Sweden. Okay, I guess I'm being racist. I don't know. All right, talk to you later.